In the last webcast, we looked at the aromatic substitution reactions of electrophilic heteroatoms. In this webcast, we're going to take a look at carbon-based electrophiles in the Friedel-Crafts alkylation and acylation reactions. One of the most useful of all the electrophilic aromatic substitution reactions is alkylation, which is the attachment of an alkyl group to a benzene ring. The Friedel-Crafts alkylation reaction is an electrophilic aromatic substitution in which the electrophile is a carbocation. Aluminum trichloride catalyzes this reaction by helping the chlorine dissociate from the carbon atom to generate an electrophilic carbocation species. The carbocation that is generated then is a strong enough electrophile to react with aromatic rings. In this example, benzene can react with isobutyl chloride to produce tert-butylbenzene in an electrophilic aromatic substitution mechanism. However, you should quickly notice that in this reaction, it is the central carbon that gets attached to the ring and not the carbon that's attached to the chlorine. Let's take a look at the mechanism to account for this substitution product. In the first step, the alkyl halide and the aluminum trichloride combine to form a Lewis acid-base complex. This complex then undergoes a hydride shift in a 1,2 rearrangement step and a dissociation of the AlCl4- species to generate the tertiary carbocation. It is this electrophile that then reacts with the benzene ring. As we know from our previous studies of carbocations, primary and secondary carbocations will rearrange rapidly if they can produce a more stable tertiary carbocation. The rearrangement of carbocation species has always been a limitation of the Friedel-Crafts alkylation. The second type of reaction that utilizes a carbon-based electrophile is known as the Friedel-Crafts acylation reaction. As a reminder, the acyl group is a simple carbonyl-based structure. Similar to many of the reactions we've seen previously, the Friedel-Crafts acylation requires a Lewis acid catalyst. Additionally, the starting materials that can be used to acylate the benzene ring can be an acyl chloride or an acid anhydride. In the presence of aluminum trichloride, either of these substrates can successfully acylate an aromatic ring. As with all the electrophilic aromatic substitution mechanisms, it's most important to understand the generation of the electrophilic species. The active electrophile that reacts with aromatic rings is the resonance stabilized acylium ion. The acylium ion is only produced in the presence of the aluminum trichloride species, and let's take a look at the mechanism of how that happens. First, the chloride of the acyl chloride species associates with the aluminum to form the Lewis acid-base complex. Following this, the chlorine dissociates from the carbonyl to generate the acylium ion. Now recall from the Friedel-Crafts alkylation mechanism in which we generated a carbocation species. Notice that the acylium ion is resonance stabilized and therefore does not undergo rearrangement. This is one advantage the acylation reaction has over the alkylation reaction.